In this video, we're going to solve integrals using trigonometric substitution. And so you might confuse a trigonometric integral with an integral that's solved using trigonometric substitution. Remember, a trigonometric integral is an integral where the integrand contains one or more trig functions. A trigonometric integral, most of the time, the integrand doesn't contain any trig functions. But it's called a trigonometric integral because what we do is we make a substitution to where that substitution involves a trig function. Okay? So when looking at an integral, how can you recognize if you want to make a trig substitution? Well, what you're looking for is you're looking for an expression that's of the form x squared plus or minus a squared or a squared plus or minus x squared. You're looking for an expression that's in that form, or it can be like manipulated or factored to be put into that form, or even like you might be able to make a pre-substitution that allows you to get it into that form. So like if you had 9 minus x plus 1 squared, well then if you said that u is equal to x plus 1, then you'd get it into that, you have 9 minus u squared, right? So you're looking for an expression like an x squared plus or minus a squared plus or minus x squared. If you have an expression like that, then you can think about making a trig substitution. And the most common scenario that you come across for these types of problems is you'll have that expression under a square root, or an even root maybe, but more commonly a square root. That's when trig substitutions are most powerful, okay? And so you've got three options. These are you're going to make one of these three trig substitutions, and this covers all possible scenarios of like an x squared plus or minus a squared or a squared plus or minus x squared. It covers all of those scenarios. So here's a squared minus x squared, here's a squared plus x squared, here's x squared minus a squared. Okay, now these are shown as under a square root because that's the most common scenario, but technically it's really more about just the a squareds minus x squareds and the term under the square root, because we're going to see, sometimes we might have like an a squared minus x squared, not under a square root, but it's squared, all that's squared. And you could use a trig substitution in that case. Okay, but the most common scenario is you have this under a square root. Okay, so when we look at this integral, the first thing you probably want to think about is, can you just make a u substitution? So like, could you say perhaps here u is equal to x squared minus 1, and so du is 2x dx, but you see that's not going to work. But we look and we see we have like an x squared minus a squared, x squared minus 1 squared. And when we see that, we think potentially a trig substitution. Particularly with the square root, we're going to see that the trig substitution is going to eliminate the square root for us. So, okay, we come to the table. That the form we have is x squared minus a squared. And so we want to say that x is equal to a secant theta. That's the appropriate substitution to make this work. A is 1 in this case, so we're going to say that x is equal to secant theta. We're going to make this substitution. You see, each of these substitutions involves a trig function. That's why it's called a trigonometric substitution. Okay, now keep in mind, we talked about this when we went through this section of the textbook, but each time you make one of these substitutions, it needs to be the case that you're dealing with a one-to-one function. And so to make the trig functions one-to-one, we need to restrict the domain, kind of like we have to do with inverse trig functions. And so in this case, we're making this substitution with the assumption that that theta is between 0 and pi over 2, or between pi and 3 pi over 2. And this is just something to keep in mind. Like for example, if we were evaluating a definite integral, and then when we made the substitution, we would update the limits of integration, then you want to check that your limits of integration are still within the domain. Okay, so dx d theta is secant theta tangent theta. So dx is secant theta tangent theta d theta. Okay, so, well, how does this help us? Well, it helps because if we take the square root of x squared minus 1 and we plug in x is equal to secant theta, we get secant squared theta minus 1. And so we see we can use this trig identity. Secant squared theta minus 1 is equal to tangent squared theta. Okay, now this is, we would put here, the technically correct answer is the absolute value of the tangent theta, because this is a principal root, right? You can have thetas, certain thetas where you get a negative, where tangent theta is negative, but with the principal root and with the fact that it's tangent squared, you can't have a positive, or you can't have a negative answer come out of this. However, because of the domain restriction, we don't have to put the absolute value. The domain restriction on theta, it only results in positive values of tangent. And so there you go. See, the square root of x squared minus 1 simplifies to tangent theta. That's the purpose of the trig substitution. And so, okay, so we've got tangent theta over secant to the 4th theta, because x is secant theta, and then dx is okay, so now simplifying, we've got secant okay, so now what do we have? This is a trigonometric integral. We solved these in the previous section. So we've got some combinations of tangents and secants. And when we have a combination of tangents and secants, we're looking for an odd power of a tangent or an even power of a secant, and we have neither of those here. And so what we do in this case is we just apply trig integrals or trig identities until we can get another form that we can solve, some other combinations of tangents and secants or whatever that we can solve. So we've got secant, tangent squared theta is secant squared theta minus 1. So okay, so we've got okay, so this 1 over secant theta is cosine theta. Okay, so we've got sine theta minus, okay, now so let's evaluate this integral. And we know how to solve any power of cosine or sine by itself. We can solve it. What we do is we say 1 minus sine squared theta cosine theta d theta. Okay, so now u is equal to sine theta. du is equal to cosine theta d theta. And so we've got 1 minus u squared du. So du minus, okay, so u minus, okay, so this is sine theta, or this is cubed, minus 1/3 sine cubed theta. Okay, so we plug this in here. We've got, this is going to be minus sine theta and then plus 1/3 sine cubed theta. So it's just 1/3 sine cubed theta. Okay, now plus c. But we need to, we're still in terms of theta, right? We need to get back to x to solve the integral. How do we do this? What we do is we make a right triangle. Okay, and this is theta. And what we do is we come back to our substitution definition. X is equal to secant theta. And what this is, it's x divided by 1 is equal to secant theta. And secant theta is, so okay, secant is opposite of cosine. Cosine is adjacent over hypotenuse, so this is hypotenuse over adjacent. So hypotenuse is x, adjacent is 1. And now what we need to do is use the Pythagorean theorem to get this side. So if this is z, then we've got 1 squared plus z squared is equal to x squared. So z is equal to the square root of x squared minus 1. Okay, so now what can we do with this? Well, we're trying to substitute here. So what we need is sine theta. Well, what is sine theta? It's opposite over hypotenuse. There we go. So what we have is 1/3 x squared minus 1 to the 1/2 power cubed. So that's x squared minus 1 to the 3/2 power over x cubed plus c. And that's it. Okay, so we see an integral, and we look to see maybe can we do a u substitution. If we said u is equal to x squared minus 1, we'd have du is equal to 2x dx, but there's no other x term outside of this. So but we see, okay, we've got this a squared minus, or x squared minus a squared here. That one of those, again, it's x squared plus or minus a squared, or a squared plus or minus x squared. We can think about a trig substitution. All right. So we've got, again, this is another, it's this form here, x squared minus a squared. We have x squared minus 1 squared. So we want to substitute that x is equal to secant theta. So we say x is equal to secant theta. So dx is equal to secant theta tangent theta d theta. And so we just did this, and we saw that the square root of x squared minus 1 is tangent theta. So that means that x squared minus 1 to the 3/2 is going to be tangent cubed theta, right? Okay. So now, okay, well, all right, we've got tangent cubed theta, which is 1. Okay, so cotangent cubed theta, right? And then, well, okay, no, let's do this because we're going to simplify it. So we'll have secant theta tangent theta all over tangent cubed theta d theta. Okay, but now let's update the limits of integration. And so what we do is we say, okay, when x is equal to 2, what is theta equal to? So inverse secant of 2 is pi over 3. Okay, inverse secant of 3, we'll just put inverse cosine of 1/3. Or no, inverse secant 3. Okay, so we've got secant theta over, okay, now we've got a combination of secants and tangents here, but the power on the secant is odd and that on the tangent is even, so we don't have any cookbook ways to solve this. We could think about substituting 1 minus secant squared theta for tangent squared, but that's not going to allow us to separate this into two separate integrals. So let's try this. Okay, so we've got 1 over cosine theta times cosine squared theta over sine squared theta. Okay, so this is so we've got a cosine theta over sine theta, that's cotangent theta. And then 1 over sine theta is cosecant theta. Okay, now the derivative of cosecant theta is minus cotangent cosecant theta. So we've got minus, this is minus cosecant theta, evaluated from pi over 3 to inverse secant 3. Okay, so we have minus cosecant, and we want to put this in. Minus 3 root 2 over 4. Okay, minus cosecant pi over 3. Minus 2 root 3 over 3. So okay, so we've got, multiply this times 3 over 3 minus 9 root 2, and then multiply this times 4 over 4. So 8 root 3 minus 9 root 2 over 12. Okay. So, here, what I notice is we could potentially do a u substitution. So if we said u is equal to 1 minus 4x squared, then du is equal to minus 8x dx. And so we could get x dx. I'm not sure why. I guess they just want us to practice trig substitution. Yeah, I think they just want us to practice trig substitution, so we're going to do a trig substitution, but the easier way would definitely be to, because look, minus 1/8 du is equal to x dx. So you would have square root of u times minus 1/8 du. So it would just be square root of u du with the 1 minus 1/8. And then you would say when x is equal to 0, u is equal to 1. When x is equal to 1/2, u is equal to 4 times 1/4, u is equal to 0. And that'd be it. But, okay, let's just assume that we don't do a u substitution. But what we see is, we see this here. And so For a trig substitution, you're looking for like that a squared plus or minus x squared, or x squared plus or minus a squared, to potentially do a trig substitution. Well, we don't see that, right? But whenever you're doing these problems, remember, you want to look for either you want to see that x squared plus or minus a squared, or a squared plus or minus x squared, or an expression that you can manipulate to put into that form. And so here, if we say that u is equal to 2x, right? So then u squared is equal to 4x squared. So this we can write as 1 minus u squared. Okay? Makes sense so far, right? Now, this is, if we say that u is like the x, then this is this form here, a squared minus x squared. And so we would make, saying that x is u, assuming x is u, we would say that u is equal to a sine theta, where a is 1 in this case. All right? So if we say that u is equal to a sine theta, so u is equal to just sine theta, but then u is equal to 2x. Therefore, x is equal to sine theta divided by 2. And that's the substitution that we want to make. That's how you figure out what the substitution is going to be. So, x is equal to 1/2 sine theta. So, dx is equal to 1/2 cosine theta d theta. Okay, so now if we make the substitution, we get, so 1 minus 4 times 1/4 sine squared theta. Okay, so we've got 1 minus sine squared theta. This is 1 minus sine squared theta is cosine squared theta. Now, we would put the absolute value of cosine theta, but because of the domain restriction was, in this case, the theta is only from minus pi over 2 to pi over 2, we don't need to put the absolute value. Okay, so we've got 1/2 sine theta, that's x, and then cosine theta, and then dx is 1/2 cosine theta d theta. Right? Now, when x is equal to 0, theta is equal to, so we've got inverse sine of 0 is just 0. And then when x is equal to 1/2, pi over 6. Okay, so we've got, we can bring out a 1/4, and then we'll have cosine squared theta sine theta d theta. And we can solve this by saying that u is equal to cosine theta, and therefore du is minus sine theta d theta, minus du is equal to sine theta d theta. Okay, so we've got u squared du, bring out the minus sign. Okay, when theta is equal to 0, u is equal to 1. When theta is equal to pi over 6, u is equal to root 3 over 2. And this is nice because we can update these limits of integration, and we're never going to have to go back. Okay, so minus 1/4. So 1/3 u cubed, and let's take out the 1/3. So minus 1/12 u cubed from 1 to root 3 over 2. Okay, so root 3 over 2 cubed is 9 over 8, and then minus 1. Okay, 9 over 8 minus 1 is 7 over 8, or 1 over 8. Okay, and so I messed this up because here, when x is equal to 1/2, we're doing inverse sine of 1. Right? Because you have to divide both sides by 1/2. So this is pi over 2. Okay, so now when theta is equal to pi over 2, u is equal to 0. So this is 0. Okay, so this is 0 minus 1. So minus 1/12 times minus 1 is 1/12.